and all other and Gopal Krishna Garu and Kavita Madam. There are many other participants also, but I would like the chairman of the Institute of Engineers, Dr. G. Venkat Subbaya Garu, to preside over the meeting, sir, to preside over the event.
Thank you, sir. Dr. K. Honorary Secretary, IA Telangana State Center. Respected keynote speaker, Dr. Martha N. Reddy, DRDO scientist and outreach teacher to the youth. Dr. K. Sitaram Babu, Honorary Secretary, IA Telangana State Center. Professor Dr. Mohammad Moinuddin, FIE committee member, IA Telangana State Center, and also the convener of today's National Science Day celebrations. Engineer B. Brahma Reddy, immediate past chairman of IEA Telangana State Center. Engineer R. Gopalakrishna Garu, other corporate members, council members, invitees, ladies and gentlemen. Good evening to all of you. Today, I feel it is a great privilege and honor to be amidst this August gathering and extend a warm and hearty welcome to the keynote speaker and all of you to this online program on National Science Day celebrations. I wish to inform that the Institution of Engineers India, Telangana State Center is organizing National Science Day on 28th February every year. The National Science Day commemorates the invention of the Raman effect by the great Indian physicist Sir Chandrakanta Venkata Raman on 28th February in the year 1928. For his discovery, Sir C.V. Raman was awarded the Nobel Prize in Physics in the year 1930. In 1986, on request from National Council for Science and Technology Communications, Government of India declared February 28th as the National Science Day. The day is celebrated to mark the important contributions made by scientists towards the development of our nation and the world as a whole. It is used to create awareness about the role of science in the society. It honors scientific achievements, inspires the future innovation, and emphasizes India's goal to use science and technology for fairer, greener, and sustainable growth. Today, Telangana State Center arranged an online program on National Science Day with the eminent expert. The technical talk is Raman Effect, Ubiquitous Practical Applications by Dr. M.N. Reddy, DRDO scientist and outreach teacher to the youth. Sir, we are very thankful, sir, for selecting the right topic on the right day. So, which is more relevant to the National Science Day celebrations. Since all of you are anxiously waiting to hear the talk from our eminent speaker, I am limiting myself and hope that you will really enjoy the talk by Dr. Martha N. Reddy Garu. On behalf of the Telangana State Center of IEI and on my own behalf, I once again extend a hearty welcome to the keynote speaker, Dr. Martha N. Reddy Garu, DRDO scientist, and all of you to this important event. So before requesting Dr. Reddy Garu to start his presentation, I request Professor Dr. Mohammad Moinuddin, convener of the event, to introduce our keynote speaker to the participants. Sir, Moinuddin Garu.
Okay. So good evening, one and all. I am Professor Moinuddin here. It is a great privilege to me to introduce today's keynote speaker, like a senior scientist from the DRDO, Dr. M.N. Reddy. He is a retired senior scientist and associate director of Laser Science and Technology Center, DRDO, Delhi. Dr. Reddy did his MSc Physics, Electronics and MPhil Physics Instrumentation from Central University, Hyderabad in 1981. and 1983 respectively. He did his PhD from IIT Kanpur in the field of laser and laser high resolution spectroscopy in 1988. He joined in this Laser Science and Technology Center, Delhi in 1989 as a scientist C and worked on several important DRDO projects and subjects. Are you getting my voice, all of you?
Yes.
Sir, yes, sir. Yes, sir. Yes, sir.
Okay. So DRDO projects and subjects, high power fiber lasers for a laser directed energy weapons, laser beam combining adaptive optics, laser spectroscopy for a standard of detection of a explosive, etc. All of these fields have been first started and have been nurtured by him in DRDO, and they now turned into leading projects. He also served as a member of DRDO think tank for a 2.5 years for a forecasting and analysis of various defense technologies. He was a visiting research scientist to the Adelphi University, New York, for a year during 1996 to 97. He superannuated in September 2018 and now settled in Gachibowli, Hyderabad. He is presently engaged in outreach teaching to the Indian youth on a scientific temperament and a skill development. He is also advising some private limited industry for technology development and manufacturing. India first and rest all next is his present campaign. So it's a great privilege and opportunity to me, sir, to introduce so to our participants. Your merit is already well known to some of other participants also. So thank you so much, Venkat Subbaiah garu. Please over to Venkat Subbaiah garu, our chairman. Hello, Venkat Subbaiah, are you getting voice? Hello.
Yeah, it's not.
Yes, sir, thank you,
Venkat
thank
Garu.
you. Thank you, Professor Mohammad Moinuddin Garu. Now I request our keynote speaker, Marthayan Reddy Garu, to start his presentation. Sir, please, sir.
Yeah. Good evening, everyone. Thanks for inviting me on this special day for Science Day talk. It's not oration, but talk. And also for a kind introduction by the organizers, the chairman, the secretary, and the convener of IEI TS Center. Definitely, I'm very happy to see some of the maybe retired much earlier faces. A couple of them I'm seeing. They are also attending. Some young people are there. I expected more to join. They will join perhaps. So I would like to maybe if I share the screen, I'm visible. Okay.
Yes, sir, you will also be visible, sir,
Yeah.
in a short screen.
Yeah, that's good. That's good.
Right, sir. Right.
Yeah. So today, as we said, we are commemorating the discovery of Raman effect. He's the only Indian scientist who was awarded with a Nobel Prize in physics, in science, in all sciences. And definitely there is a lot of importance to be given. Though, in my opinion, that was today we can say small discovery. Even Sir C.V. Raman couldn't have expected that how it has transformed into a myriad of application areas in terms of analytical instruments in many fields. And I also would like to mention one thing that I have shown here, one instrument. So why I'm interested to talk on this day, why I'm a little eligible to talk on this very day, is that generally we, whenever we celebrate in various R&D, government and R&D institutions, various topics will be talked. Not much on the Raman spectroscopy or Raman effect, but when I was serving as a scientist in DRDO in Delhi, this is not my main task. This is let's say, a sort of hobby I started with, and the spin-off resulted in terms of the first engineered backscattered Raman spectrometer for detection of standoff detection of various explosives, detection and identification of explosives which have been produced in numbers, maybe 250 or 300 of them so far, and they have been distributed to IB of our security agencies successfully. So what I wanted to say, this is the first time many people are working, almost every laboratory is working without Raman. They can't do any research, at least in the material science and chemistry. But unfortunately, all these spectrometers have been imported till today. So this is the commercial grade kind of development. And it has inbuilt small computer. Of course, it's a laser based. We will discuss a little later. But this is complete in itself. And you just shine you just switch on and shine the laser passing through the transmitter, and it recollects in backscattered, recollects and analyzes the scatter and detects the Raman fingerprint, Raman chemical fingerprint, and then identifies it. So as you see, there is some spectra also attached to this. Definitely, this we should celebrate as a event to boost the morale of the young scientist and the youth, particularly to spread scientific temperament. That is most important, and the spirits of science. And I have been doing it in my own way, going to schools, colleges, talking about science and the science behind the technologies. Obviously, we all know that science is only for enriching our knowledge. And of course, that will make us an empowered citizen, definitely. But it is the technology that is going to enrich our country, economy, and provide us better standard of living. So it is the technologies, but without science, you can't develop any technology. So knowing science, applied research is imminent for developing any technologies. Of late, I think the competition is, the criticality is very, very high, because whatever was to be done by many of our institutions, research institutions, R&D institutions, and academia. But now the cutting edge technologies that are required for the country for self-reliance, definitely it is a big challenge. That is why, as you might be knowing, DRDO is put under restructuring, but none other than by our Prime Minister. And it might be going from Ministry of Defense to Prime Minister. So that means we must keep it in mind that scientific temper is very much important. So how to instill the scientific temper in the young minds so that they'll become very motivated towards the R&D and applied R&D and develop skills, and then get some inspiration from accomplishers, and then definitely they will grow much into the technology field and develop technologies that are required for the country. Okay. Okay. Why it's not? Okay. Yeah. Yes. As I said, Raman wouldn't have imagined that this effect is going to have this much impact. So, well diversified myriad of applications in analytical instrumentation. Of course, it is also very simpler compared to many other instruments. But Raman spectroscopy and microscopy, earlier it used to be only Raman effect, is converted into Raman spectroscopy to study the materials. We'll come to know to identify the let's say compound, the crystal structures, and then constraints, how they are part of the compound. So as a chemical fingerprint, but then now many of these spectroscopy instruments have been converted into microscopy, microscopy. Now they can also image the material and defects, and the vast number of applications are there, definitely in material characterization and investigation. Properties, to know properties, and particularly of these days nano materials, wafers. And the biggest benefit of Raman effect goes to let's say biology and medical diagnostics. In fact, without Raman, there is no medical college, there is no bioscience, life science laboratory, and there is no, I should say, the hospital, because it has got plenty of applications and unique applications. We'll discuss a little later, but definitely it has given so much of impetus to the diagnostics, particularly in biosensing. Pharmaceutical industry, definitely, definitely it is a chemical, so it will investigate its, distribution, and then its structure. Food and agriculture industry, definitely it is also going to, detect the soil, and then the food quality. Environmental science definitely is going to detect pollution control, and then humidity, temperatures, many other things. Combustion diagnostics. Yes, Raman spectroscopy is also used for studying the combustion, and then flames at high velocities, where other probes could not be inserted, and to measure the or characterize the flame. So it helps so much. Maybe let's say we are testing the aero engine, and the nozzle flame will be at very high temperature and speed. We can't approach, we can't put probes this way, because Raman spectroscopy is non-contact, non-invasive. It is standoff. So, and in situ. So because of it is in situ, it has got a lot many applications. We don't have to make samples, sample preparation for testing the sample, because we send the laser, and then we get the backscattered and or in forward also. The explosives, drugs, counterfeit, all and chemical warfare agents can be detected and identified. That's what I made my hobby project into a commercial equipment. Then obviously this is very suitable for forensic analysis. Once you want to find out what is the contamination of the explosive environment. So this is the right one. Gemology, gem. I think the quality and the other defects they can do. Geology, mineralogy, semiconductor, solar energy, because they're all going to find out the crystal and the structure, and then defects, as I said, and then the orientation of the crystals and many other things. Wavelength conversion. So Raman was earlier used only as a spectroscopy, but Raman has become now a laser also. Raman lasers, Raman amplifiers are really playing big role, and the future lies in Raman amplifiers for long-haul telecommunications. Because right now we are using erbium-doped fiber laser amplifiers to extend the signal to reduce the signal attenuation and amplify the signals maybe over 600 meters, but Raman amplifier are going to be much easier than that, and it will take more than thousands of kilometers before amplifying the attenuated signal. So since it is a science day, we can spend some time on a general topic, and we can sprinkle here and there different topics. As it is mentioned here, science today is the technology tomorrow. Definitely, we all know one scientific invention can change the world forever. It has happened. We all know that there are many transformative changes because of some unique inventions, like right from the beginning, if we know wheel and spin mill, and then steam engine, and then transistor of whole electronics, and then since I am from the optics, photonics, even photonics has become a big field like electronics, and then nanotechnology definitely, and then Raman definitely is a big discovery for the investigation of materials of all kinds, not only solids, liquids, powders, biosamples in aqueous conditions as well, and in vivo as well. It is really revolutionizing the analytical world. And as we see that the light microscopes and then telescopes have gone to very high resolution, you can see somewhere here the atoms today, and which no one expected to see them. We are going down to 0.5 nanometers resolution. Yeah. Just to mention about what is science, what is technology and systems, and many of us may have some doubts, but definitely science is only for acquisition of knowledge, what is all around us in the universe. And but one good definition which I say, science is nothing but common sense at its best, that is rigidly accurate in observation and merciless to the fallacy of logic. Yeah, so absolutely there is no fallacy for the logic. It has to be rational. It has to be logical. So that is what when I teach, when I teach scientific temper to the general public, that we must observe ourselves. We should not take anything on face value. And then obviously investigation, scientific methodology is there. We must follow some of them, but we should not take anything. But one even better definition I would like to read out, none other than by Edwin Hubble. Equipped with his five senses, man explores the universe around him and calls the adventure science. Such a beautiful quotation. So we have five senses, and then whatever we observe and explore, it is nothing but science that we are following it. Okay, going further, generally I tell kids when I go to school, so they must first cultivate for asking questions, and also using these three questions: what is it, why is it, and how is it? They must inquire. Then only they will understand. If they just know what is it, is they will pass the examination. Why is it, they don't ask it. And how is it, hardly they go into it. So I always tell them, if they want to learn anything, let's say how aeroplane, what is it, how, and aeroplane, how it works, and what is the application, and so know how, know why, kind of situation in terms of technologies. Yeah, scientific temper is very much part of our constitution. To develop the scientific temper and humanism and the spirit of inquiry and reforms is written in our constitution as the 8th fundamental right, but it refers to an attitude of logical and rational thinking. And it must have all these ingredients: inquisitiveness, spirit of inquiry is very much important. So I keep telling on this National Science Day, inculcating scientific temper in the masses is very important, and it is responsibility on all of the highly educated scientific community. So further going, just wanted to tell, these two instruments you see, one is a microscope, another is telescope. In fact, have got everything what we knew so far. The telescope, through telescope, we saw the wonders of the the sky and the cosmology. We know whatever is known is due to the telescope. And whatever we know at microscope level, let us say at a subcellular level, in biology, in microorganisms, in virus, even nano particles. So it is because of the microscope. These two instruments are very important. Just coming to before coming to the real topic, what I wanted to know, because many of the participants may not be familiar with the spectroscopy. We all know that every element. To start with, I should tell that in this world, in this universe, nothing is static. Everything is moving or vibrating, whether it is a structure, whether it is a planet, whether it is a element, whether it is anything, whether it's a house, whether it's a brick, whether it is a molecule, even molecule. So the electrons within the molecules have got bonds, attached with the atoms. So they are vibrating, and the atoms, the electrons moving around, and they have certain energies when they are revolving around the nucleus. So when we give some energy, they emit. So this is emission spectroscopy. Long back, people used to do in the micro slides. And these are fingerprints of these elements. Likewise, for molecular species, the vibrational energies, because molecule has got various bonds, various types of bonds. The compounds have many type of molecules, multiple molecules. They have different bonds. They have, and their strength and length will be different, and so they'll be vibrating. So the vibrational energy, if we can determine that, those are the fingerprints of the molecule. So Raman spectroscopy, exactly, we do the same thing. So this is what the telescope we found how the light emitted by the stars and other have gone, they shifted, blue shifted, red shifted because of the, Doppler. So we came to know they are moving away or coming closer, kind of thing. Okay, now coming to the main topic, here we are going to use light because we said it is non-invasive, non-contact. It is only possible with a sort of radiation. So now invisible, we call the electromagnetic radiation as light. And as we know that light has got a quanta of, we call it photons, and it has energy and momentum depending on its frequency from gamma rays to the microwaves and RF. So the properties of light, we all know that reflection, refraction, diffraction, interference. So interference is the most fundamental one. And obviously the scattering, polarization, absorption, transmission, wavelength, energy moment, which I told. So these are the mechanisms it will undergo when we shine or when it interacts with the matter. So most of the physics, what we came to know is through light matter interaction. So Raman also is also a scattering, a kind of scattering. So we call it inelastic scattering. But we have seen a lot of scattering. Why the sky is blue? Because it is a Rayleigh scattering. It scatters blue light, high frequency blue light, more by the atmospheric constituents, particularly molecules and other particles, which are of the order of wavelength or 1.5 of wavelength, more than the lower, the higher wavelengths. That is why is blue. And why it is not, violet and other things, definitely there are some absorptions. They are called the electronic absorptions, much above the atmospheric. When sunlight is coming, they are observed. That is why it is more like light blue rather than dark blue. And as we said, the scattering goes like 1 over lambda to the power of 4. So the higher the lambda, so red is least scattered, then the blue is maximum scattered. That is how we see the blue. And we see red when sun is setting, because blue is scattered away, and then only passing light is red. So as we see here, already it was told that the Raman effect is nothing but detection of scattered light by the molecules of a compound when we shine, when we incident, when we make a monochromatic light incident or irradiate a sample, any kind of sample, as I said, liquid, sample, crystal, solid, powders. This excites. The mechanism is a little quantum mechanical, but semi-classical, we can say that. Because this light has some frequency, as it is mentioned here, and it excites the electrons in the which are in the molecule, and because of this the electromagnetic radiation has got electric field, it will create a oscillating dipole, because electrons are oscillating, and since that is so when oscillating what is the dipole moment is there, it is supposed to radiate at the same frequency. So that is further modulated by the intrinsic vibrational frequency. As I told, every molecule or every compound has got molecules, and every molecule has got atoms connected with the bonds. So these, because of that, they are vibrating in different ways. And this vibrational frequency is a fingerprint of that material. So when we shine light, so the light induced dipole moment, when it is re-radiated at the same frequency, that is called Rayleigh scattering. But that is modulated by the intrinsic vibrational frequency. So we get this plus minus incident frequency. So one we call Stokes, another we call the anti-Stokes. As we see here, unfortunately, they are not active here. So this is the Raman spectrum for each bond. This is methane, CH4, and you can see for each type of bond, you will get a peak. You will get a peak, Raman peak. These are all Raman peak, and this is the fingerprint, chemical fingerprint. And using this, we can find out the internal structure of the molecules, and then many other properties. But unfortunately, this is a very weak phenomenon. Only one photon out of 10 to the power of 7 photons, incident photons, will result into Raman. So that is why earlier people were using IR spectrum, IR spectra, FTIR, we call spectroscopy of most of the chemists use it, either in the transmission or in the reflectance. Basically, it is a absorption spectroscopy, which is a complementary, rather it was work hard. So if you go to any chemistry or material science laboratory, you will find both FTIR and Raman, they are complementary. They give the same thing, but Raman is better in many ways because their resolutions are very high, and some bonds don't give the absorption. So they are found out in Raman, for example, homonuclear the molecules like nitrogen, oxygen. So as we see here, as I said, any molecule will have the electrons having their energy levels. For example, this is the ground state. This is next vibrational state. The electronic states are very high, actually. Only UV, violet, blue will absorb little bit, but this the visible and IR will not be absorbed. So that is why this FTIR, they use absorption spectroscopy. But in Raman, what happens? We send it is a very easier method than the absorption spectroscopy, which requires a tunable wavelength source. Here you can take any wavelength in, let us say, in visible or even in UV or near infrared. So generally we take here 532 nanometers emitting from the laser diode. And you see, when we shine and this is excited, the molecule is excited, means the vibrational state of the molecule is is excited to a virtual state. They are not a bound state, the virtual state, because we are taking randomly any wavelength. And from there, it comes back to the same ground state, then it emits the same wavelength. So it is called a Rayleigh wavelength. And then in another case, what happens, it goes to the same kind of virtual state, but it comes to the next excited vibrational state. So the difference is, gives, the red-shifted photon. That means that less frequency, but higher wavelength. So we call it Stokes. So as you see here, this is my, the black one. This is recorded by me perhaps in, I don't know, this is the, not, this is the, what is that, the digital storage ASCO model, but it is done somewhere in 17 or so. These are called anti-Stokes. These are. So the otherwise, if the molecule is excited from the upper state, next excited state, to the further higher virtual state, and it lands back to the ground state, it emits with higher, a photon with higher energy. So this is called blue shifted. So you will get the Stokes here, you get the anti-Stokes here. So as you see here, see these bonds are just rotating, vibrating, rotating. Even rotational also gives. For every vibration, you have a Raman peak. And this is measured in a centimeter inverse. It is the energy, or you can measure in nanometers also. And each one is a fingerprint of that molecule. So, so this is what Raman has seen. So laser shined on the sample, and he could observe instead of the same wavelength, same color light, he saw two different colors, but very, very faint. The greatness goes to him is because that time he had very rudimentary instruments. Today we have very sensitive modern equipment. We are able to do it within a half an hour, this kind of experiment. But Raman had a passion for studying the liquids, and so he has been on the job for a very long time. So he developed to see these two faint lights, the photons or light, using his equipment, what we saw on the first slide. And he immediately reported, perhaps sometimes in April 1928. There are many stories, but definitely one story is that this effect, this is inelastic scattering of light by the samples, by material, by chemical compounds, is anticipated, predicted by some Austrian scientist much earlier, maybe 1823, but unfortunately he couldn't publish it. And there is another group in Russia also detected it, but they reported, they published little late. So this is, so it was not shared. The Nobel Prize is not shared. So Raman could do the one, but nowadays I think our scientists are not, of course, forget about the inventing, but then innovations, they must register as patents, and I think there is a drive of late. So Raman just found out spontaneous Raman or normal Raman. Just he shined with mercury arc lamp and on some materials, on benzene perhaps, and then detected. And that is called normal Raman. Because of the, invention of the laser, now, there's a big impetus to this Raman spectroscopy. Now, so many variants, you see, there are 10 variants are there doing the same thing, or much amplified Raman signals provide very important information, many applications, particularly in biology. And the notable ones are, of course, microscopy, FT Raman, resonant Raman. So we are all talking about virtual levels, energy levels, but definitely if you match your excitation wavelength with a bound state, a real vibrational excited state or electronic state, vibrational state of excited electronic state, there will be big amplification, maybe 10 to the power of 4 times of the spontaneous Raman. Stimulated Raman also is the one which provides amplification. There is, as I said, coherent anti-Stokes Raman spectroscopy has been developed. It is a very powerful diagnostic tool for, as I said, for detecting the temperature profiles and concentration profiles in high temperature plasmas, flames. So many applications in aero industry and other industry. And surface enhanced Raman spectroscopy is the another one which has given really a big boost to this the analytical Raman spectroscopy instrumentation, that it amplifies almost 10 to the power of 8, and sometimes people quote it 10 to the power of 12 times. So single molecules is also the reported detection of single molecules using this. And these are all one, but definitely the last one, you see, Raman lasers, Raman amplifiers are going to really give us a big... See the fingerprint, Raman, for example, here it seems just taken from the literature, mean component. And here it is saying how much percent of fat, protein, water, this one. And it gives these peaks. Of course, these are little broad, but definitely each peak corresponds to a particular bond of the species in that material. So people used to investigate all kind of matter, not only for research but in industry, as I said. See, these are the ones which my own after retirement I did some work on this. For example, sulfur Raman spectrum. So nice peaks over here. Sulfur, will have something like 8 atoms kind of thing, and then so each peak, but then excitation will be at 0. So it is not mentioned here. Excitation will be here. So this is Raman shift, what we call. These are Raman shift 1, 2, 3, 4. Any 2 Raman shift will give you complete information about the identity of that material. Here you see naphthalene Raman spectrum. So nice peaks, unlike in absorption spectroscopy. So let us say this is RDX. This is done by us in Delhi. You can see such nice Raman peaks, providing the information about how the molecular structure of RDX. And you don't have to know all of them. If you know 2 of them, 2 separations, I said Raman shift. If you know 2 separations, you will find out by taking the ratio, you will find out the chemical structure, and thereby the identification of the, let us say, explosive of the materials. See, some of the Raman one. See, this is ice, and this is and in seawater. So there is a marked difference here, and here also Rayleigh also shifts actually, and So like this, so water, ice, and dry ice. So very different studies. Though it is shifted even a few, centimeter inwards, that is sufficient to find out it. So like here, water temperature also. If water is 1.5 degree Celsius and water is 0.5, and the Raman structure is. So Raman spectroscopy not only provides you the the chemical structure or composition of the chemical compound, but it will provide the phase also, the internal state of the matter, whether it is in solid form or there is a phase transition, and what is the temperature at and what is the density, all sort of internal state of the matter also. So it is very important study in solids semiconductors. So for example, here, silicon, you need single crystal wafers, and if it is little amorphous, you can see so much different. This single crystal, poly, and this amorphous. So the peaks, this is the wavelength it is given, but generally it is given in a centimeter inverse, and you can convert into this one, and this difference is sufficient to know the defects and the quality of the wafers. You see, Raman microscopy is now doing a big revolution in the biology and medical diagnostics. As you see, you don't have to have a label-free detection, scanning, because earlier people have to, give little label chromophores, which so give fluorescence, some dyes to attach to the, let's say, malignant or suspicious tissue or organ, and then irradiate the laser, and then the healthy one and diseased one is to. So here Raman you don't have to do, because you can always find out which is healthy tissue, because it is going to give the cellular what is that, the structure it is going to give you. So as a result, which is the healthy tissue, which is the diseased tissue, and also Raman microscopy is giving you disease markers. So that is why in vivo Raman microscopy has become a very powerful tool these days. Raman never imagined. Raman just found out, observed, two different wavelengths when you shine light on the benzene with one wavelength, one monochromatic wavelength, and he found out. And actual development of based on Raman effect started in from 1930 itself, but the big impetus has come to this when laser was invented in 1960. Okay, so just to tell you why we are using laser, and maybe I should skip many of this one. And the laser is definitely light amplification by stimulated emission of radiation. Why I'm telling what kind of lasers to be used in a Raman spectrometer, and how they are going to enhance the specificity and sensitivity. So we all know that lasers are there everywhere, and of course in defense, I worked for high power fiber lasers, which have got a lot of application as a alternative weapon. And then definitely lasers are everywhere, maybe optoelectronics. So these are nothing but a intense collimated monochromatic beams, and they can be developed. Definitely every light, every photon is developed by a material. So lasers also developed by some chosen materials, and chosen materials will chosen wavelengths. And so you need an active medium, that is a material. So it can be semiconductor, it can be crystal, it can be even gas, ion lasers, all and even liquid lasers are there. And then now we talk a little bit about the semiconductor laser because they have got the highest efficiency and then very cheap, and then they are developed to very narrow line width, which are very important for using as excitation source in Raman spectroscopy. So there is a, you see, medium, active medium, and the active medium is excited by some mechanism, either by electronic excitation or optical excitation, by another laser or arc lamp, flash lamps, excite these crystals, for example, neodymium ion laser. So they use these flash lamps to excite this. The first laser was ruby laser. So ruby crystal was here, and then they wound that, the flash lamp tube, and then it excites those atoms. See, electron is excited means atom is excited. So excite to the higher energy levels, and then when it comes back, it emits a photon. So that we call it is incandescent one. But Raman is done. Raman emission. Sorry, the laser emission is by stimulated. That is where it is very unique, and it has got some spectacular characteristics which we decide. And then this light emitted from this active medium, so is kept in a we called optical cavity or resonator. So to give you the optical, what is the positive feedback? So we are making the amplifier into oscillator. So laser is nothing but an oscillator, and you keep on pumping the material, and the light or photons emitted in this one, they go back and forth. These are reflectors. This is a very high reflector, 99 or 100% reflector, and this is partially reflected, so that when the light field builds up, light passes, leaks out as a laser. And there are some conditions to laze. Definitely the length of the resonator should be integral multiple of half wavelength. That is how the standing waves are formed. Okay, we'll go this what. So ground state, my material excited here, and it is here. And then it stays here for a very short time, this lifetime. So sometimes it is nanoseconds, in some cases in microsecond, milliseconds. And so after that it falls back, because any thing in the world, it wants to occupy the lowest energy state, isn't it? We all come down even when excited. So it is same with the quantum particles, electrons, and these atoms. So it is same, like we throw a stone in the sky, it comes back, it won't stay there. So here also it spends very these excited states and comes back, and it emits a photon equivalent to h nu or hf, and f is the frequency, and you can convert into lambda. And but what happens when already photon is the atom or molecule is excited in the upper state, and then you pass one let us say a photon with the same frequency of this delta E energy equivalent to delta E, then what happens? It triggers, it stimulates this one, the molecule or atom back to the ground state, and it emits another photon with the same state. That means phase, direction, polarization, of course, wavelength and frequency. This is what happens. So same thing happens in many are there in the upper state, and then one photon, one atom decays spontaneously, and that triggers all the other excited atoms back to the ground state, giving rise to the photons, each one photons which are in phase. So that is why the light is very coherent. And then different materials will have different states, 3-level state, 4-level state, so which we don't want to go. But definitely laser has got, I said the cavity. So TEM00, Gaussian mode. This is the best plane wave actually. So lasers can be transmitted to moon even longer, and we use in the defense. We want to engage, let's say, some target up to 8 kilometers. So we need a laser with a very good beam quality. So this is the TM00 mode, and these are higher order modes, and they diverge soon. And whereas this one will not diverge soon, and it can be focused to a very small. So same thing what you see in the fiber optics communication. You are sending the light pulses through the fiber through single mode and multi-mode, and definitely single mode has a lot of advantages. So here also same thing, but then these materials have got the gain. They have some gain. Semiconductor has some gain, and other lasers have got some gain. Only those longitudinal modes, because we said standing waves, each one forms a modes, and that means each one they're all emitting throughout the cavity length infinite number of wavelengths. But those wavelengths will survive, which are supported by the gain medium. So they have a gain actually here, and otherwise loss. This exceeds the losses occur in the cavity. That is why this survives, and then you will have single or few modes. So lasers are highly bright and intense radiation, highly monochromatic, even single color, coherent, both spatial and temporal, highly directional, as I said, low divergence, highly polarized. You can use this property in many applications, including in the Raman, and then communication, and wavelengths are tunable many ways. In fact, if you can employ tunable laser, you can scan different, let us say, the cells to get, label-free Raman signals. But generally, we use fixed wavelength laser, and then different type of molecules will give rise to different colors, the different wavelengths, and that is taken into, using software. They will give the colors and identify. They are, continuous wave or short pulse. They have gone up to even attosecond, not pentosecond, femtosecond, attosecond, and they are modulable. As I so lasers are all there. So many lasers. I have mentioned here that there are Raman lasers also there, because today we are talking what. So I'm giving you a little introduction to the lasers as well, because laser is the one which has revolutionized the spectroscopy, not only Raman, but all kind of light spectroscopy and many areas. So the semiconductor lasers are very important. Fiber lasers are very important, but Raman lasers, various kind of lasers are there, and they can be nanosecond pulse lasers, microsecond pulse laser, quasi CW laser, CW lasers. When it comes to semiconductor lasers, they can emit in all wavelengths, right from, let us say, 380 to even 2 micron, that is 2000 nanometers. Here, the communication wavelength you have 1300 to 15 wavelength. So indium, gallium, arsenide, phosphide. These are all compound semiconductors, and they are not direct. They are indirect. They are direct to band gap semiconductor, not silicon or germanium, which are direct, indirect band gap, and momentum is not conserved there when they emit it. So most of the the excitation or a recombination, from the conduction band to valence band, the electrons, when they recombine, right, as you know, they emit light. And if they are indirect band gap, it emits into thermal radiation, maybe phonons. As you see here, I don't want to go into details, but definitely you can see all sort of lasers. So the here I'm showing you these colorful one. The small lasers have come of late commercially. So much of innovation in development of diode lasers or diode pumped solid state laser. We call DPSS, and definitely diode pumps a solid state crystal, and that will emit much better quality laser at a different frequency. And further, it is converted, it is doubled, tripled, or even fourth harmonic generations are there, fifth harmonic are there, using some crystals, nonlinear crystals. So it's all, I don't want to go into the details because these are all quantum well lasers. See, the emitting medium here is particularly a semiconductor epi layer, and of late multiple quantum well lasers have come. They are much more efficient than previously just p-n junction kind of lasers. As you see here, from conduction band to valence band at certain forward voltage, there will be a lot of electrons in the conduction band, and a lot of vacancies, that is holes here. And when you give sufficiently high voltage, of course they are heavily doped, so they recombine and emit radiation. And as I said, it is a stimulated emission, so you can get. So any semiconductor laser, to start with, if you pass small current, it works like a LED, and then it shoots up, and then it becomes so narrow, this laser, and then it will be powerful. There are several types of laser, edge emitting laser, vertical cavity lasers, and this has become very, very important, and a lot of research still going on, improving this vertical cavity surface emitting VCSEL, and in different wavelengths. And this is a multiple quantum well laser, and the beam quality is much better than this edge emitting lasers. And as I said, you have see the ordinary, you have ordinary, the pointer, green pointer, is not a diode laser, but is a diode pumped solid state laser. As you see, even 100 rupees worth laser has got so much of assembly and innovation here. You have a diode here, and a diode focuses here on a crystal ND5V4, and that emits, let us say these diodes are the 808 nanometers, and then you will get 1064 nanometer because of this crystal, and that you will use a KTP crystal is used to double it. So 1064 nanometer will become 532 nanometer, which is green. So the green light, what you get is this one, and I don't know, people must be seeing, and it is a almost 200 milliwatt laser. You can get these today for 500 rupees in Delhi, or even online, maybe 1,000 rupees. And only 10, 12 years back, this much of laser with this kind of power used to cost not less than 40,000 rupees. Like computers, they have become. So tunable lasers also possible. You have a DFB laser, distributed feedback laser, external cavity laser, all lasers are there. Okay, so how these lasers are used to detect, let us say here I'm going to give the explosives, and that too from a distance. You are not going to touch, or not going to very close, and these are the challenges. You need sensitivity because their vapor phase is very, very minute. PPB, PPT kind of vapor phase. So unless you impinge on the laser impinge on the solid material, you will not find out. So resolution, so you have to have a good resolution. So laser wavelength should be line width should be narrow, and the Raman obviously peak should be very narrow to identify whether it is a TNT, DNT. Response will be very fast if you want to make a screening, the screening of personnel in the airport and elevator. It should be very fast, and there should not be false alarm. Whether false positive or false negative should not be there. Portability, they should be handheld. We started interacting with the security agencies, and first they were very bulk, and then we went on miniaturizing. But even now they are, let us say, 2 kgs, and but definitely we reduced from 7 kgs to 2 kgs, and some new designs are there which will make them much. They wanted just to use them to check the suspected suspicious items. Explosives are often hidden, tightly packed. Vapor pressures are very low, and there are many other.
Mathareddy garu,
Sir?
Mathareddy garu,
Yeah.
Sitaram Babu sir, please close in 10 minutes, sir. Please.
Yeah, I'll complete in 10 minutes. Okay.
Okay, sir. Thank you. Thank you.
Yeah. Okay. So it is very, very, very challenging to develop such a Raman-based explosive detection, standoff explosive detections, because we got to detect sometimes contamination of the residues on the surfaces. Okay, which I told, and we just started with little, as I said, this is a hobby experiment started in the lab, just like here. And this is the laser on the bench top, and started exciting with the 532 nanometer. And then we use some commercial spectrometer to detect. So this is the, as you see here, CCL4 to start with to optimize the sensitivity. And then here we find, you see, this is benzene and nitrobenzene. You see, one is non-explosive, another is little toxic and explosive. And here, as you see, DNT and TNT, the peaks are differed by very small margin, maybe 7 centimeter inverse. That is sufficient, because our Raman spectrometers have got the ability of resolving even 3 nanometers, 3 centimeter inverse. And so you can selectively identify the materials. Okay, this is what it was looking to start with when we launched. I think the screen is blocked by the other one. Hopefully you are seeing it, but I'm not able to see. But this is one, HMX, another highly sensitive explosive. We developed it 2007. And then just to tell you before, what is the schematic, optical schematic? Generally, what you need a laser like this, you need a spectrometer. These days, those days, very big spectrometer. These are, CCD charge coupled CCD devices are there. And this looks like this. This is a CCD spectrometer. What it does is you send some light, let us say several wavelengths, and it will detect different wavelengths, identifies different wavelengths. Spectrograph it is. It is not a monochromator, spectrograph. So what happens here? First, we have a laser. It is reflected off by some mirror, which is coated for this wavelength, and this is a dichroic mirror. That means it reflects. And then there is a focusing assembly transmitter and focus on the material. And then Raman scattered light, the back scattered light comes here, it passes this one, and we put some filter so that everything is filtered out except the expected say high pass filter, this in optics, edge filter, and then you have a lens over here, you focus that, and then that light got several components, it will give you the spectrum like this. Okay, so this is the one. And sometimes we use a pulse laser to sense very sensitively, ppm, 100 ppm from 2 meters RDX using a pulse laser, but this is a tabletop, as you see over here. This is the R&D exercise to optimize. Of course, many people wanted to find out, detect from 50 kilometers. In fact, it is possible, but a little difficult, which we have done it. So these instrument, Raman-based instrument, which I said different versions are there. That was the first one. This is the second. This is the third. This is the fourth. This is rather in between. And this is the latest one, which is not yet fabricated, is only designed, palm held kind of thing. So this is how it works. I have a video also. Raman is there. You shine. It is the testing in the laboratory. This is a full version of the Raman spectrometer on a sample kept over here, and sufficient. The inbuilt computer is there for, and then peak finding algorithm is there, and then what we put Raman. What do you call? Spectra database already existing, or you can create them. Then when you get this kind of spectra, you compare with them and find out, assign the peaks to certain particular bonds. And from there you can find out, okay, this is naphthalene. So it can tell you, and I have a video of that also. So same thing, RDX and TNT, when you process these peaks, sometimes will have fluorescence if the material is also fluorescing. And that is why people move from 530 to 785, where fluorescence is not predominant. That is why different wavelengths are required. This was the one we designed, developed. One this one a prototype, but after I left, what happened I do not know, but definitely these are all the latest one, and this was handed over by none other than then Defense Minister Mr. Arun Jaitley to the IB personnel long back, and now there is a big group created. I started sometimes in 2007 as a hobby. Now 2 groups are working on that for further. But these days, of course, we are much safer. Microscopy, of course, it looks like this. Basically attaching this spectrometer to a conventional microscope with attachments, and then microscopy provides the imaging of the Raman excited samples, and you can easily find out whether they are diseased or the what is that healthy as far as the biology is concerned. But here they are RDX and PE10 kind of things they are found out. The other one which I was telling, another version is coherent Raman spectrometer. Coherent anti-Stokes Raman spectroscopy, which I said, of course, the schematic is very cumbersome. You use 2-3 lasers, and that is good enough to get the anti-Stokes Raman to diagnose or to characterize these plasmas and flames, or the combustion, high pressure, high temperature combustion. The other one is SERS, surface enhanced Raman spectrometry. Here the analytes, the species that we want to they absorbed on some the metal coated surfaces, their nano particulate matter on the substrate, and there the electric field will be what the trapped, and then the increased several folds. As a result, the signal is amplified. So surface enhanced Raman spectroscopy, it is a very challenging, and a lot of work is happening in DRDO and other places, and yet to in India yet to fabricate a system, commercial viable system, but tabletop systems are there, which is very useful for vapor detection because the explosives are in vapor. I have got
Sir,
last
we'll close, sir. Sir,
three-
Mathareddy garu.
three slides.
Okay.
Okay, this is the Raman laser. You can create, you can convert Raman shifted frequency into laser using stimulated emission. So these days you can have, that means you can have lasers at any frequency. That is how we are using, WDM, high capacity, fiber optics networks, long haul communication. We modulate, demodulate, but when signals are traveling over thousands of kilometers, they are attenuated. So you use amplifiers. Earlier, converters, you are using it, repeaters you are using. Now we monolithic kind of amplifiers we use. Earlier, erbium doped amplifiers at the same wavelength. But then now we use Raman kind of wavelengths. See, there are a lot of advantages over EDFA, erbium doped fiber amplifiers, than to Raman amplifiers. Raman amplifiers, you don't have to have a separate, fiber and spliced to the communication fiber. Same silica fiber is used to generate phonon based Raman signatures, and they are amplified under stimulated action and thereby increased. And this is the last one. And you can use Raman lidars also. You can find out, the atmosphere. You can high altitude atmosphere and the clouds. What is the temperature profile? And then even atmospheric species, even pollution monitoring. But I think Raman is used mostly for temperature, pressure profiles. So thank you very much.
Thank you, sir. Sir. Thank you very much, sir. So you have given an excellent lecture, sir, today. So most of the people just know what is meant by Raman effect only. But today you have explained elaboratively what is the Raman effect and what are the applications. Even today I don't know, sir. This is the technique used in case of explosive detectors. And you have very well explained about the lasers also, sir. You have started with the basic science, entered into engineering, and extended into the technology which we are using today, sir. Thank you very much, sir, for your excellent and extraordinary and elaborative
just
lecture.
Put a little too much of it, and maybe it was not required, but definitely the Raman effect has diversified into so many, I said, ubiquitous applications. I wanted to just bring out, but definitely it is a little elaborative, but not in detail.
But,
I can take some questions, queries.
Yes, sir. So from the participants, if anybody is having any questions, please ask our speaker.
I do not know. I have what is that video? Will it work if I do? You can't see now?
No,
Can you
sir.
see?
No, sir. We can't see now.
Oh, you can't see. Okay, that means I should have done it in um, you know, in a. Oh,
Okay, sir. In the another occasion, we will go through that also. And in
I'm
future
seeing
also, we will invite you, sir.
how to get back to Zoom.
Sir, I think, as you said, sir, we'll plan for one day event, sir. Why don't you make yourself free? We are planning.
Yeah, that's right.
We can plan. We're planning to have 1 day and 2 day workshops, sir, at Institute of Engineers physical event. That will be a physical event. I think whatever you are trying to, I think that will be more helpful for college students, sir. We'd like to invite them on a larger scale, sir. I think probably the bigger number will come, sir. I think this you can probably store it for students, sir.
Okay, definitely.
Okay, sir. Right. Thank you, sir. Thank you very much.
Yeah.
Sir, now I request our Honorary Secretary, Dr. K. Sitaram Babu Garu, to propose vote of thanks.
Thank you. Thank you very much, Martha Reddy garu. As you have said, we'll stand by it, sir. We're going to conduct 1 day and 2 day program, sir. And take the opportunity to call you at the appropriate event, sir. That will be basically electronic, sir.
Yeah.
And I should also thank for having given time and make sure that you had a very extended talk on Raman effect ubiquitous practical application, sir. I think most of the audience for today, I think probably would have enjoyed, sir. And I also should thank the chairman for and the convener of the event, Mohammad Mohiuddin Garu, and our chairman, very prestigious chairman of Institute of Engineers, Dr. G. Venkat Subbiah Garu, for having made this National Science Day as an event, sir, and calling you and appreciate your presence here, sir. We also individually thank I mean, most of the participants here, sir. Dr. Ramna Naik Bant Garu is our civil member, sir, committee member. Dr. Gajarana is production committee member. Dr. Rahim Ahmad, Sheikh Shafi, engineer D. Rama. She's from basically civil, sir. Irfan, Kavita, Srinivas Rao, Mulsuru. And so I think a few of them already joined, sir. But I think because of the extended talk, I think some of them already left. But anyway, sir, all said and done, it's a wonderful topic, sir. We look forward to have your session at IE. And before we wind up, sir, let's stand up for national anthem, sir. Thank you.
Okay, thank you very much.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय हे
Jai Hind.
Jai Hind. Okay, sir. Thank you very much. Thank you very much, and thank everyone who have viewed. And then definitely we keep meeting and interacting as you said.
Sure, sir. Sure, sir.
Thank you,
Thank you,
sir.
one and all.
Martha Reddy garu.